Scientists have long marveled at the secrets of the universe. However, the more they discover, the much more they realize they haven't even started scratching the surface. Much of the limitation is the capacity of the equipment astronomers are using, which has restricted our knowledge horizon. However, there is new space equipment in town, and scientists are getting ready to be amazed by the findings they will make. The new James Webb Space Telescope promises to open up even more exciting parts of deep space, and some of them are terrifying. In fact, in this video, we bring you James Webb Space Telescope's terrifying discovery at the very edge of the universe. What is at the edge of the universe? That question cannot be adequately answered without first answering the question of the dimensions of the universe. So just how large is the universe? The answer is actually a moving target. This is because the universe is expanding and gravitating, so any answer must consider these two concepts. But that doesn't mean we can't arrive at an estimate. When you look to greater and greater distances, you see things as they were, not only far away but also back in time, owing to the finite speed of light. The more distant universe is less clumpy and more uniform, having had less time to form larger, more complicated structures that require more time for gravita's effects to take place. To arrive at the size of the universe today, there are actually three things to consider. One, how quickly the universe is expanding today, something we can measure via several methods. Two, how hot the universe is today, which we know from looking at the radiation of the cosmic microwave background. And three, what the universe is made out of, including matter, radiation, neutrinos, antimatter, dark energy, and more. So by taking the universe we have today, we can extrapolate back to the earliest stages of the hot Big Bang and arrive at a figure for both the age and the size of the universe together. We will kill two birds with one stone. From observations available, including the cosmic microwave background, supernova data, large-scale structure surveys, and baryon-acoustic oscillations, we get our universe is 13.8 billion years after the Big Bang, now 46.1 billion light-years in radius. Any farther than that, and even something moving at the speed of light since the moment of the hot Big Bang will not have had sufficient time to reach us. As time goes on, the age and the size of the universe will increase, but there will always be a limit to what we can observe. So what is at the edge of the universe? We might be able to see stars with the naked eye, but the edge of the universe is another thing entirely. This is where the James Webb Space Telescope comes in. Did you know James Webb, who the new space telescope is named after, was the second NASA administrator? He is best known for heading up Apollo, the first space program to send humans to the moon. He was also instrumental in the two crewed space programs after Apollo, Mercury and Gemini. While Webb eventually died in 1992, aged 85, he left a massive legacy behind, deserving of a telescope named after him. And truly, a personality of the stature of James Webb deserves such a powerful telescope. Often referred to as the successor of the Hubble Space Telescope, the JWST is the largest space observatory ever built. Its gigantic sunshield base measures a massive 22 meters by 12 meters, about the size of a tennis court. However, even though it is nearly twice as big as Hubble, which is only 13 meters long, the JWST is almost half by weight at only 6,500 kilograms. The JWST's gold-plated mirrors have a total diameter of 6.5 meters, much larger than Hubble's 2.4-meter diameter plate. This means the JWST will have approximately a 15 times wider view than Hubble. You've heard different comparisons of JWST with Hubble, but the two iconic telescopes function differently. The Hubble's primary focus is on both visible and ultraviolet light. It has some infrared capability, but it is nowhere near the extent to which the JWST can. In fact, the JWST is designed to work on the infrared spectrum. This means it can't see in ultraviolet light as the Hubble, but it can focus on bright objects like very distant galaxies. But distant galaxies are not the limit for JWST. It can observe objects that are over 13.6 billion light-years away. This means we will look back 13.6 billion years, which brings us between 100 and 215 million years close to the Big Bang. Most of the size of the JWST is due to its large sunshield. It is so big that NASA engineers had to design it to unfold during the launch because of space limitation on the launch vehicle, and then unfurl it while it journeyed to the permanent orbit. This is used on all space telescopes but is especially important with the JWST due to its infrared cameras. If it isn't kept cool enough, it stands the risk of blinding itself to the lights of objects it is trying to observe. One other key difference between the two satellites is their distance. The Hubble telescope orbited above Earth's atmosphere but was near enough to be approached if repairs needed to be done. But the JWST is many magnitudes further away, around 1.5 million kilometers away. That places it farther than any human can and has ventured, meaning nobody can call on it for a repair if something goes wrong. NASA chose the location for a few reasons. It will be in a place where the gravity of the Sun and Earth work together to help keep the satellite in place. Plus, it will be far away from the reflected radiation of the Earth, helping keep it cool. The JWST will technically orbit the Sun, but the orbit is not stable and will decay. But the thrusters aboard the Space Observatory will correct the orbit periodically. After a month's journey during which it deployed many of its instruments, thankfully with no issues, NASA has been configuring and calibrating the different components on the telescope. It has sent back the very first images which the space agency has combined to form a composite image. This is by no means close to what the JWST is capable of, but the mosaic took a whole week to capture and consisted of 1,560 images, amounting to a massive 54 gigabytes of raw data. During the 2 decades the JWST will work, scientists have many aims for the JWST, including examining the first light in the universe and the celestial objects which formed shortly after the Big Bang, investigating how galaxies form and evolve, studying the atmospheres of distant exoplanets, capturing images of planets in our own solar system, locate evidence of dark matter, searching the edge of the universe, and the list goes on. When that last one happens, that is, when astronomers train the JWST at the edge of the universe, what will they see? Remember we said that the universe is 46.1 billion light-years in radius. That is the limit of the observable universe. There is much more out there. How do we know what lies out there beyond the observable universe? We can make inferences based on the laws of physics that we know and by using the things we can measure within our observable universe. For instance, we observe that the universe is spatially flat on the largest scales. It's neither positively nor negatively curved to a precision of 0.25%. If our current laws of physics are correct, we can set limits on how large, at least, the universe must be before it curves back on itself. We can get the best data for our extrapolation from observations from the Sloan Digital Sky Survey and the Planck satellite. The two sources suggest that if the universe does curve back in on itself and close, the part we can see is so indistinguishable from uncurved, it must be at least 250 times the radius of the observable part. This leads to the conclusion that the unobservable universe, assuming bearing any topological weirdness, must be at least 23 trillion light-years in diameter. It must contain a volume of space that is over 15 million times as large as the volume we can observe. However, there are compelling arguments that the unobservable universe should be significantly even bigger than that. How? It's like this. The Hot Big Bang might mark the beginning of the observable universe as we know it, but it doesn't mark the birth of space and time itself. This is because before the Big Bang, the universe underwent a period of cosmic inflation. Rather than being filled with matter and radiation and being hot, the universe was filled with energy inherent to space itself, expanding at a constant exponential rate and creating new space so quickly that the smallest physical length scale, the Planck length, would be stretched to the size of the presently observable universe every 10 raised to the power of -32 seconds. Sure, inflation stopped in our region of the universe. However, 3 key questions that directly affect how large our universe is remain unanswered. These questions deal with whether the universe is infinite or not. They are: 1. How big was the region of the universe post-inflation that created our hot Big Bang? 2. Is the idea of eternal inflation, where the universe inflates eternally into the future in at least some regions, correct? And 3. How long did inflation go on before its end and the resultant hot Big Bang? It is possible that the universe where inflation occurred barely attained a size larger than what we can observe. Perhaps any year from now, the evidence for an edge to where inflation happened will materialize, and we will have to adjust our perception of the universe again. But it is just possible that there are plenty of universes out there just like ours, following the same laws of physics and having the same types of physical, cosmic structures. This raises the tantalizing possibility of complex life in one of the numerous worlds out there. There should also be a finite size and scale to the bubble in which inflation ended, and an exponentially massive number of such bubbles contained within the larger inflating space-time. Let's hear what you think about what the JWST will uncover in space in the comments section below.